Hello everyone. Today we are going to discuss one of the most important topic of graph theory, which is known as planar graph. This particular lecture material has been prepared based on the syllabus of graph theory paper 8B of MSc Mathematics course organized by Netaji Subhash Open University. So the entire lecture is basically, we have divided into 5 or 6 important points. So today we will be covering introduction to planar graph, planarity of K5 and K33, Kuratowski's theorem, characterization of planar graphs and Euler's formula, and some consequences of Euler's formula. So let's start with the first module called Introduction to Planar Graph. So before we get into the further detail of definitions and other diagrams, this is very important to know why we should learn this topic, planar graph. Everyone knows that graph theory is a very important application in most of the applied science division as well as engineering divisions. So we have a lot of application in several places. So just to tell you about the importance of this particular topic, I have actually given a case study. So let's start with that case study first. The case study is, recent statistics has shown that the number of accidents has significantly increased in some of the roads of a crowded city. Moreover, it has been observed maximum accidents occur in those points where the roads cross each other. These points are referred as conflicting point. The City Development Authority engaged a reputed civil engineering firm to reduce the accident mainly occurring in the conflicting points without building many more flyovers. Now this is the problem statement and the engineering firm needs to resolve that issue. So they have come up with a resolution. Let's see what is that. So the resolution is, so after a few days, the chief engineer of the company has met the city planning officer and said, you know what, we don't need to build any flyover, we just need to change the orientation of few roads. The good news is, we have found a planar graph with all the roads having the conflicting points. Oh, it's awesome solution. Now what is this planar graph? That we need to definitely know. So let's define the planar graph first. A graph is called planar if it can be drawn in the plane in such a way that no two edges cross. So we have given 3 different examples of planar graphs. The first one, obviously there is no edge crossing in graph A, so it is planar. Again in graph B also there is no edge crossing, so that is again a planar graph. Interestingly, the graph C, which has some edge crossing, in the first look the diagonal edges cross. Now we need to relook it and we need to redraw it, whether is there any other way to draw that graph C so that the edge crossing will be deleted, so or edge crossing will be avoided. So let's draw the third graph in a different manner. So oh yes, there is a way that we can always draw it without the edge crossing. So it looks like it's a planar graph. Now if we redraw it, and then what will happen, we actually created that graph C, which is isomorphic to graph B. It's similar to graph B. So we can redefine the planar graph concept like a graph is planar if it is isomorphic to a graph that can be drawn in the plane in such a way that no two edges cross. Now we need to discuss the planarity of K5 and K33. These are the basic building blocks of planar graph. So these are very important implication, because based on these particular theorems, or based on the planarity of K5 and K33, we will conclude a lot of things about other non-planar graphs. So is K5 planar? That is the question. Is K33 is planar? That is even another question. So to actually prove whether that is the K5 and K33 is planar or not, we need to know some definition before we proceed. So the definition 1, it is a Jordan curve definition. Given any 2 points A and B in the plane, any non-self intersecting continuous curve from A to B is called a Jordan curve, and it is denoted by Jordan A to B. If A equals to B, that is the starting and ending point are the same, then J is called a closed Jordan curve. So we have given 4 different curves just below this particular definition. The first one, it is obviously continuous. When I say continuous, it means we can draw that particular graph with pencil. We do not need to lift that pencil from the paper. We can still smoothly draw it. Similarly, the second one is also continuous. The third one is also continuous. The fourth one is also continuous. Now, what about the closeness? The first one, it is not closed because the starting and ending points are completely different. The second one is also not closed. The third one, yes, it is closed because the starting and ending point are same, and the fourth one is also closed. Now we need to check out of these 4 graphs which are basically non-intersecting. The first one, it is not self-intersecting. The second one is also the same. The third one is self-intersecting. And the fourth one is basically not self-intersecting. So if we go by the definition of Jordan curve, the first graph, the second graph and the fourth graph, they are all Jordan curve, but the third one, which is self-intersecting graph, that is not a Jordan curve. So the final conclusion is these 3 are Jordan curve. The first and second are normal Jordan curve, and the fourth one is the closed Jordan curve. Now let's start the Jordan curve theorem. Any closed Jordan curve J partition the entire plane into 3 parts, namely interior of J, another one is exterior of J, and the third one is the J itself. If P be a point in the interior J and Q be a point in the exterior J, then any Jordan curve J dashed from P to Q contains a point of J, that is J dash intersect J. So if we see the diagram, the J is a closed Jordan curve, and it splitted the entire region into 3 different parts, interior, exterior and the J itself. P is in the interior part and Q is in the exterior part. So PQ is another Jordan J dash. Definitely J dash will intersect J. Now there is a corollary of this theorem that is also very simple. J is closed Jordan curve in a plane, then 2 points PQ of J are joined by another Jordan curve J dashed in the plane. And these 2, J dashed and J, doesn't have any other point common apart from P and Q. So we can say that the J dash is entirely contained either in the interior of J or in the exterior of J. So the figure actually tells that story. So either PQ may be in the inside or in the outside. So now it is in the outside. So these are the corollary of Jordan curve theorem. Now based on this Jordan curve theorem and corollary, we will prove now whether the K5 is planar or not. And K5 is basically a complete graph of 5 different vertices, right? So the graph G has 5 vertices, A, B, C, D, E. So we are joining those A, B, B, C, D, D, E, A. Now if you see the figure, this A, B, C, D, A, E is basically a closed Jordan. So this is a closed Jordan and it divides the entire plane into 3 parts, interior, exterior and the curve itself. Let's see what are the remaining edges for K5. So I have marked it in a dotted line, all the remaining edges. Now if you look properly, then we can see that each of these 5 remaining edges are basically another Jordan curve. Now since that let's say the AC is a Jordan curve and ABCDE is a closed Jordan. According to the Jordan corollary, we can always say, since A and C is on the closed Jordan ABCDE, so we can always say AC Jordan curve will either inside the closed Jordan ABCDE or in the outside of closed Jordan ABCDE. So these edges are also considered to be Jordan curve. Now, by pigeonhole principle, out of this 5 dotted edge, if we use pigeonhole principle, we can always say that at least 3 of them will be either inside or outside the closed curve. So, you know, that is very obvious, because if we have 5 different balls and we have 2 different pockets, then definitely one of the pocket will definitely contain at least 3 balls. So that's the basic idea of pigeonhole principle, and it's a very famous principle in mathematics. So using that, let's assume that either 3 of them is inside or outside. So the case 1, there are at least 3 curves inside G. So I have marked it in the red line. I have not drawn it yet, but just I have indicated those 3 curves. Now connect AC and AD. Now assume F be a very close point, F be a point which is very close to B. So why we have considered it? Because we have considered F is very close to B, so that there is no intersection in between B and F. So that means F is very, very close to B. Now if we try to apply the Jordan theorem, we can see that F is a point which is inside the closed Jordan ABC, and D is another point which is the point which is outside the closed Jordan ABC. So if we connect F and D, that particular edge will definitely intersect with AC. So we can say that this for case 1, definitely there will be edge crossing, right? So now FD curve will intersect AC. So similarly for case 2, we can do the same thing. So we have F, in case 2 we have considered all the 3 edges AC, AD and BD is basically drawn through the outside region. So initially we have connected AC and AD, and we have considered a point F which is very close to B, and now if we connect F and D by the similar argument, we can say that this particular FD Jordan curve also will intersect the AC Jordan, right? So even for the case 2, we can say that it has some kind of edge crossing. So using Jordan curve and corollary and the pigeonhole principle, we have concluded that K5 is not planar graph. By similar argument, using the same theorems, we can always show that K33 also is a non-planar graph. So it is the same thing. In K33 is basically a bipartite graph. It has 6 vertices and every vertex has degree 3. So we can show that also. So I have left that as an exercise to the viewers. So now we have already proved that our K5 and K33 both are non-planar graph using topological argument. Okay. So now we have few remarks based on our previous analysis. If G and H are 2 different graphs, then, and let's assume H is a subgraph of G, and then if G is a planar graph, then that implies H is also planar. And this reasoning is very obvious. The reason is H is a subgraph of G. So we are assuming that G is planar. And how do we create H? We create H by selective deletion of some edges and vertices from G. So there is no point of additional crossing. So if G is a planar graph, then definitely the subset is also a planar. Similarly, if H is a subset of G, or rather G is actually superset of H, and if the H is non-planar, then G is also non-planar. Why? The reason is very simple. Since G is superset of H, So we are, and already we are assuming that H is non-planar, and we are actually making G by adding few more vertices or edges. So already we have some H crossing in H that is still there in G. So therefore, as J is a supergraph, so therefore G is also non-planar. So these two things are hereditary property. So if the subgraph is non-planar, then the corresponding supergraph is also non-planar, and if the supergraph is planar, then the corresponding subgraph is also planar. Therefore, we have already proved that K5 and K33 is non-planar. So any supergraphs of K5 and K33 is also non-planar using the remark 2. So we have actually drawn a particular Venn diagram which is basically a superset of K5 and K33. Now, as of now, we have seen all these elements inside this Venn diagram are basically the supergraph of K5 and K33, and since K5 and K33 are non-planar, we have proven that this entire set is also non-planar. Now the question is there any larger set of non-planar graphs? So is there any other graphs which is non-planar even if they are not supergraph of K5 and K33? That is the question, and that we need to answer in the remaining slides.